Hello dear learners, we are studying about UV visible spectroscopy and this is lecture 2. In this lecture we are going to study about the chromophores and the Beer and Lambert's law. Now the term chromophore. The group of atoms containing electrons responsible for the absorption is called chromophore. Most of the simple unconjugated chromophores give rise to the high energy transitions of little use. For example, ethylenes, acetylenes, carbonyls, nitriles, azo compounds, etc. These substances are called as chromophoric substances. Now, oxochromes. The substituents that themselves do not absorb the ultraviolet radiations, but their presence shifts the absorption maximum to the longer wavelength are called as oxochromes. The substituents like methyl, hydroxyl, alkoxy, halogen, amino groups, etc. are some examples of oxochromes. Now, let us see about the other terminologies: bathochromic shift or redshift. It means a shift of an absorption maximum towards the longer wavelength or lower energy wavelength. Hypsochromic shift or blue shift, a shift of an absorption maximum towards the shorter wavelength or higher energy. This we can see by this diagram, that is bathochromic shift, hypsochromic shift, another is hyperchromic shift and hypochromic shift. Hyperchromic shift is occurring due to the result in a decreased absorption intensity, and which is because of the introduction of the group destroying the geometry of the molecule, and because of this we are saying the hypochromic shift. And hyperchromic shift will result in the increased absorption intensity of the compound. Now, the basic of the absorption spectroscopy is your Beer's and Lambert's law. So first we will see about the Lambert's law. When a beam of monochromatic radiation passes through a homogeneous absorbing medium, the intensity of the radiation decreases proportionally to the change in the thickness of the absorbing medium. Means what? The radiation which is passing through the homogeneous medium or the substance to be studied under UV spectroscopy, the intensity of the radiation depends on the thickness of the absorbing medium, and it can be written mathematically as minus di upon dt is proportional to I, where di by dt is equal to ki, where capital K is the proportionality constant, I is the intensity of the incident light, T is the thickness of the medium. By integration of the equation 1 and by putting I0 and when T0 is equal to 2, we get the equation I0 by IT is equal to KT, and where I0 is the intensity of the incident light, IT is the intensity of the transmitted light, and small k is the constant which depends upon the wavelength and the absorbing medium used. By changing the above equation to the natural log, we get IT is equal to I0 into e raised to minus KT, where capital K is equal to K by 2.203. So we get IT is equal to I0 into I0 raised to minus 4.4 minus 0.4343 KT. Now, another law is Beer's law. This relates the high absorption and the concentration of the absorbing substance. That means here only the thickness of the solution is not considered, here also considered the concentration of the absorbing medium. Intensity of the incident light decreases exponentially as the concentration of the absorbing medium increases arithmetically, and its relation between the light absorptive capacity and concentration of the absorbing species is there. The above sentence is very similar to the Lambert's law, which you have already seen. So IT is equal to I0 into K raised to minus e raised to minus K dash C, where IT is equal to I0 into 10 raised to minus 0.4343 K dash C, and we get the equation upon solving That is, IT is equal to I0 into 10 raised to capital K dash C, where K dash are the proportionality constants, C is the concentration, and by combining the equation 3 and 4, we get I0 by IT is equal to 10 raised to ACB, where A or epsilon is there and C is the concentration. And epsilon is the absorptivity, which is a constant which depends upon the lambda, that is the wavelength of the incident radiation and nature of the absorbing material. The value of epsilon depend upon the method of expression of the concentration. The ratio of I0 upon IT is termed as transmittance T, and the ratio log I0 upon IT is termed as absorbance A. Formerly, absorbance was termed as optical density or extinction coefficient E. Thus, we can also write capital A is equal to log I0 by IT, and by combining the equations 5 and 6, we can write down A is equal to epsilon EC, and it also can be represented at the molar absorptivity. Thus, the absorbance is the product of absorptivity, optical path length, and the concentration of the solution. The term even 1% 1 centimeter refers to the absorbance of 1 centimeter layer of the solution whose concentration is 1% at the specified wavelength. According to the equation 7, A is equal to log of I0 upon IT, and we can write down the transmittance as I0 upon IT, and we will see about the deviations of the law. The Beer's and Lambert's law maintains the linearity under the specific conditions only. The law makes inaccurate measurements at the higher concentrations as the molecules of the analyte exhibit stronger intermolecular and electrostatic interactions, which is due to the lesser amount of space between the molecules. The presence of fluorescent compounds also cause deviations. Use of polychromatic radiations may give incorrect results. The formation of solute and solvent complexes may also result in the deviation, that is the polymerization. And this was all about the UV spectroscopy, the laws, it is the Beer and Lambert law, and the various terminologies or various concepts like chromophores and auxochromes. Thank you for listening.